Okay, so welcome everyone. Welcome to Flower Monthly for June. It's great to get the community together again, and so rapidly after Flower Summit that was just last week. But it's a good chance for us to kind of gather together and hear from two really interesting speakers that I'm joined with today, Javier and Berivan. And so just to remind us though what Flower Monthly is about, it's a monthly get together of the community. We do it virtually, and we try to do it on the same time, same day of the month. And so it's the first Wednesday of the month at 1600 UTC. So that corresponds to 9 a.m., for example, in San Francisco, 5 p.m. London, midnight for Beijing. And the whole idea is an informal get together where we can share different types of material. So sometimes we might have announcements with the framework. Sometimes we might have invited speakers like we have today talking about their research. Other times we provide tutorials and how-tos about how to use the framework in different settings. And so as always, your suggestions are welcome. This is a community-driven endeavor. And so if there are different things you'd like to see as part of Flower Monthly, just let us know. And so we have a dedicated channel, for example, in our Slack to get suggestions and to discuss things as Flower Monthly is happening. But I just want to say, please give us feedback and we can sort of evolve this venue as it goes on. But for June, this edition of Flower Monthly, we have this agenda. And so we're beginning with a few welcoming messages. And then I'm going to give you a very brief recap of the Flower Summit that was just last week, the third Flower Summit that we've had thus far. And then after a brief recap, we're going to hear from our two invited speakers that I mentioned earlier. So we are joined today by Berivan Izzik of Stanford University. He will be talking about work she's been doing with collaborators all around the world, actually. People in Italy, people in the UK. And this is a piece of work that was presented at ICLR. And she'll also be telling us a bit more about also how she engages with her work in federated learning more broadly, I think. And then after we hear from her, we have the latest member, in fact, of Flower Labs. We have Javier, who's going to speak to us about how does he approach simulation when it comes to using Flower. And so I'm super excited to see all the different tips and tricks and approaches he's going to tell us about today. So fantastic monthly. But let's kick things off with a very brief recap of Flower Summit. It was an incredible event. I was so excited to see the community out in force last week. As I mentioned, it's the third time we've run Flower Summit, and we had record numbers. Most of those numbers were joining online from around the world. We had well over 550 people register and attend at different times. We also had a great physical attendance this year. And so almost all our speakers, for example, were attending in the Cambridge location where we brought everyone together to do most of the presentations. And so just to kind of, if I wanted to give you one slide snapshot of last week, this 2-day event, it would be this slide here. And so this year we moved from doing a single day event to a 2-day event. We just had so much demand for people who want to show different dimensions of how they're using Flower or how they're investigating the world of federated learning, that we had to expand it out to 2 days. And so we had a research day that involved around 18 different institutions from around the world who presented primarily research-driven results in the area of federated learning using Flower. And so we had folks such as institutions from the UK, from the States. We had people flying in from South Korea, all around Europe, the West Coast, the East Coast, to present on that first day their research results. And on the second day, we had a very similar sort of recipe, but it was more industry focused. one of the real drivers for us to expand out to 2 days was that we had a lot of new types of use cases from people in various companies. So we had representatives from Bosch, Intel, Brave, Banking Circle, just to name a few, that were presenting ways that they're using Flower to examine federated learning. We even had people from the Air Force join us who presented some of the educational material and the program that they've developed that uses Flower to educate folks in the Air Force. And we had an exciting opening talk from Catherine at ThoughtWorks about the security dimension to building these distributed federated systems. Daniel, or that many of you know, and who's on the call today, he presented two different platform updates, one research focused and one industry focused on both days. And then while I'm giving you just sort of an overview of what happened last week, the primary thing I want to say is here's a snapshot of the event. If you weren't able to join us on the live stream or in person, over the next few weeks, we're going to be releasing a series of videos that capture all the research talks, all the industry day events and announcements and presentations, of the platform updates, and everything you would have seen at the event is going to be released over the coming weeks, in case you didn't quite catch all of it. My slide just changed heading. Is it still looking fine?
I think it is not full screen anymore.
Oh, strange. I think my browser crashed mid-presentation. Let me just switch back. Okay. The way that the sandwich between these 2 days was a networking event at the Tivoli. You see this on the left-hand side. It was a fantastic event where people could socialize between the 2 days. There was golf on hand for those who are interested. And then two other additional components to the event that we sort of introduced this year were a much expanded range of tutorials. And so we had tutorials for beginners, we had tutorials for research specific use cases such as iOS support, simulation. We had tutorials about how do you go transition from an industrial centralized use case to a federated one. So the plenty of tutorials, they're going to be released. And we also had 4 big announcements on the platform that I'll be summarizing in a few slides' time. But that's sort of that's the overview. And I want to just briefly show you some of the images from the day. So we gave out swag. You can see images from the social events. And then there was an exciting, there's an exciting point in the morning whereby we announced a new initiative called the Summer of Reproducibility. And while we'll be announcing more details about this later this month, we assigned 2 winners from the Flower community already, whose contributions to baselines had been such that we needed to really reward them under this new framework of Summer Reproducibility, and say that they were Pedro Guzmão, and you can see Pedro on the top left-hand image here, receiving a check for $2,000 based on his contribution to enhancing the reproducibility of federated learning under the Flower framework. The other winner was from the University of Avignon in France. That was Man Nguyen. For he's a student-sided group there who works a lot on speech recognition, and they produced an important new baseline in the direction of self-supervised learning that was integrated quite recently. Other images you see from the day, we had Stefanos from Brave, we had the tutorials you see in the middle there. We had Chancellor from the Air Force on the bottom right, presenting all the different ways that they are using federated learning in their industries or organizations. And so I'm going to teaser. It's basically a teaser for the summit that was fantastic last week, where you'll be able to see these videos and documents and so on, talking about all the different announcements coming up this month, by just summarizing 4 key announcements that we made on the platform. The first was called Flower Ops, which is basically overviewing a variety of existing tooling out there that we are building compatibility with for Flower. So an example of this would be weights and biases. That's an important type of tool that people need to use to optimize their hyperparameters. And so there was actually a presentation by Weights and Biases during the event on how you can use that important piece of infrastructure in Flower when you're trying to optimize your federated learning example. We also announced, as I mentioned, the Summer Reproducibility. This is going to be a 3-month initiative whereby we want to have community contributions that we're going to reward from a pool of up to $100,000 as people produce baselines that will enhance the ability of the federated learning community at large to do reproducible science. And so there was going to be further announcements on this effort. We also announced Dandelion, which is our project name for a partnership between Brave and Flower, where the ambition is to eventually have all Brave browsers capable of being used in a federated learning system to support personalization features and so on. And so although this initiative is just getting going, the eventual ambition would be to have the upwards of 60 million different browsers working together in a federated learning system. And of course, because it's being powered by the Flower Federated Learning Framework, it's be open source. And in that context, it'll be the world's largest example of open source federated learning to date. And finally, we made a 4th announcement of a system that's going to be in preview release over summer. It's called FedGPT. And the idea here is to enable federated learning to fine-tune LLMs. And this will allow people who have private sensitive data to fine-tune publicly available open source backbones, things like Llama and Bloom, towards a customized LLM for their use case without sharing the sensitive data with a third party. It's in preview release during summer. And so if you're interested in getting access to this early preview release, there's a URL here. But my main message again is these 4 announcements that were made. If you're unfortunately not able to attend the summit, over the coming few weeks, you're going to see the videos and other material released that kind of provide you with all the information. So with that sort of teaser about the Flower Summit, I'm now going to hand over to our first invited speaker of today. And so our first invited speaker is Berivan. I actually met her about 6 weeks ago or 2 months ago, perhaps, at this wonderful Hugging Face organized event where they were trying to really bring the open source AI community together. And in short order, they had 5,000 people all come in one place. So we were there, a lot of other AI open source companies were there, and also a lot of researchers were there. And that's where I started talking to her about her interest in federated learning, her application of Flower. And so it was an ideal situation here to invite her to present her work today. So thank you so much for coming today. We're really delighted to hear about your work and connect you with the rest of the community.
Yeah, thank you so much for inviting me. Can I share screen?
Yes, if I stop sharing, then I believe you'll be able to start sharing.
Okay.
Yeah, we can see the screen. Looks great.
Okay, cool. So thanks again for having me here today. I'm a PhD student at Stanford, and I'm working on federated learning, distributed learning. And I will talk about our ICLR 2023 paper today. So before I give details about our work specifically, I will first go over some sparsification methods that are mainly used for model compression after training. And then I will show you how they have been adapted for federated learning to improve communication efficiency. So one very commonly used method is model pruning. Again, here we are talking about centralized learning. So as usual, we first randomly initialize the weights, we train them to full convergence, and we achieve some good accuracy, let's say 90% accuracy. And then to compress the model, we set the smallest weights to 0. So we prune sometimes 90, sometimes 95% of the weights. And this method works surprisingly well, and we are mostly able to achieve the same accuracy even after pruning. So magnitude is only one salience metric. There are some other ways, but like looking at magnitude is just so simple, and it works surprisingly well in practice. And it's a very common method to compress pre-trained models. And this method has also been like adapted for the federated learning setting. So one very simple way to use pruning to improve communication efficiency is to actually prune the model update. So at every round, the client updates their local model, and then before they communicate their updates to the server, they can just set the smallest ones to 0 and gain some communication efficiency. Or there are more complicated ways to use pruning, as in this slide. So for example, here in these two works, the server initializes the network, and then it sends this network to a client. The client alone performs some training and then finds a pruning mask. And then the federated learning stage starts. So all the clients actually tries to train this prune model. So it has maybe advantages and disadvantages. So one disadvantage is we rely on one client to do some training until full convergence and extract a good pruning mask. So that's, I think, like one piece of this work that has less motivation maybe. And another line of work, again, like I'm switching back to the centralized setting, the lottery ticket hypothesis. So in this paper, what they try to test is, like they ask this following question. So we are able to train a network and prune maybe more than 90% of the parameters, and we are able to preserve the accuracy. So let's say we extract this subnetwork at the end. Then they ask this question, like, what if we start with this architecture in the beginning? So what if like we actually use this subnetwork architecture with randomly initialized weights, would we be able to get the same accuracy? And it turned out that it's not possible to get the same accuracy. But then they performed another experiment where they still like keep the same subnetwork architecture. But they didn't randomly initialize the weights, and instead they used the same initialization that they used in the beginning. And with this approach, they were able to achieve the same accuracy. So it's interesting. It just suggests that we know that we can actually start with a very sparse subnetwork, and we can only train that network to achieve the same performance. But the initialization is very important. The initialization and the subnetwork architectures are connected in some way. And the only way to find the correct subnetwork architecture for now is to first train the full network to full convergence, which is not very efficient. So there is still some ongoing research on that. And then, of course, it was also like adapted for federated learning to improve communication efficiency. But so I'm just referencing one paper here. They have the same like slight drawback here. So their idea is like at every round, each client will train some local model, and they assume that the clients can train these models to full convergence and then extract lottery ticket networks, which may not be reasonable in practice, because the clients have limited data, and we don't know if they can train these models to full convergence and extract lottery ticket networks. Okay, so there is the third sparsification approach, which is more recent than the other two. So again, we are in the centralized setting. And these two papers I'm referencing, they tried like similar experiments. And what they do is like they randomly initialize a network. So this network has all random weights, and they never train the parameters. Instead, they find some connections. They extract some connections from this network. So, and they end up with a subnetwork, but with random weights. And they show that this subnetwork can achieve really good performance. So for example, I'm just showing some figures from the first paper here. So the orange and this dark blue curves are performance of the train full network. It's not the subnetwork, it's the full network, and we train the parameters. And the red and the light blue curves, so they almost achieve the same performance. And what we do here is like we never train the parameters and we find subnetworks with different sparsity. So for example, here the best performance is when we keep almost like 50% of the weights in the subnetwork. And the only difference between the red and the blue curve is how we initialize the random weights. So this seems like an interesting empirical observation. And there is also some theoretical work where they studied how large the initial dense network should be so that we can find a subnetwork with a certain depth. So it's theoretically and empirically motivated. It's an interesting observation because we never even train the parameters. We are just exploiting the fact that these models are too over-parameterized, and we can even find subnetworks that works well with the random weights. So in this talk, I will talk about our work that tries to adapt this approach to federated setting. But different from prior work, we will not rely on the client to train a model to full convergence because we don't think it's realistic. And also, we are not doing it just for the sake of showing an adaptation of this method in federated learning. We will actually use it to improve communication efficiency. Okay, so our goal is to find these subnetworks with random weights, collaboratively across clients on clients' non-IID dataset. So we are in the full federated setting. The clients have non-IID dataset. There is partial participation and everything. And we will do it in a communication efficient way. So we want to spend less than 1 bit per parameter. Whereas in the traditional, the standard federated learning, we have to use at least 32 bits per parameter to communicate model updates. And empirically, we will show that our method converges faster than other methods that operate around the same bit rate. And we will also have end up with an efficient representation of the final model. And I guess the idea is now more or less clear because I already explained the centralized setting. So the server will initialize a dense network with random weights, and all the clients will also have the same randomly weighted dense network with using the same random seed, basically. So each party has the same dense network with random weights, and everyone freezes the parameters. So they will, throughout training, they will keep the random weights frozen. And instead, the clients will train a probability mask, which has the same architecture as the dense network. So this probability mask has these connections with values between 0 and 1, and each connection corresponds to the probability that the corresponding connection staying in the subnetwork or not. So for example, if this value is close to 1, that means that with high probability, this connection will stay in the subnetwork at the end. So our goal is to train this probability mask. And then, so let's say the clients, let's say we have a probability mask that is trained to some level, and at the inference time or during training at forward pass time, what we do is we extract a binary mask from the probability mask. And the way how we do it is we sample a binary mask from the Bernoulli distribution parameterized by the probability mask. And then this binary mask, again, of course, has the same architecture as the dense network. And it has values only zeros and ones. And using that binary mask, we can actually extract a subnetwork. So we basically multiply the binary mask with the dense network, and we end up with a subnetwork with random weights. And then this subnetwork is used during forward pass. And so if it's during training, then we also compute a loss function. And then we backpropagate this loss function to update the probabilities in the probability mask. And we never touch the actual parameters of the dense network. So the clients perform these iterations, these operations for a number of iterations at every round. And at the end of each round, they end up with their local probability mask. And ideally, they want to communicate this mask to the server. And again, ideally, what we want to have at the server is the average of these probability masks to update the global probability mask. But we want to do it in a communication efficient way. So therefore, like the clients will not communicate this probability mask directly. They will try to communicate a compressed version of this. And what we propose there is actually the same operation that we used during forward pass. So they each client, once they compute their local probability mask, they will take a binary sample from their Bernoulli distribution parameterized by their local probability mask. And then this binary mask has the same number of parameters as the probability mask, but now it only has zeros and ones. So it only has to communicate at most 1 bit per parameter now. And then the server's estimate is just aggregate of the binary masks instead of the probability masks themselves. So here I said we only need to communicate 1 bit per parameter for each client, but we can actually reduce this number significantly. So in our iClear paper, we propose some entropy coding methods to further compress it and like reduce the bit rate to about 0.8 bits per parameter. And the way, the reason why it works is the entropy of this binary mask is actually not 1, it's smaller than 1. And the reason is these values, zeros and ones, are not equally distributed. So there is no symmetry here. And what we observe in practice is most of the parameters in the binary masks are actually 0. And because of this asymmetry, the entropy is actually smaller than 1. And with entropy coding methods, we can actually reduce the bit rate down to that value. And then we have a follow-up work, which is not out yet. There we are actually reducing the bit rate down to 0.1 bit per parameter. So it's more than 10 times improvement, and it will be out soon. And hopefully you will also like our results there. So, okay, so the server's estimate is the aggregate of the binary masks, but ideally what we want to have is the aggregate of the probability masks. And we can show that this estimate is unbiased. And we can also upper bound the error of this estimate. And these are necessary properties to prove some convergence results. So we can actually claim that the model will converge to the same point because we have an unbiased estimate and upper bounded error. Okay, so one last point I want to make is, so in this work, of course, weight initialization is very critical because we initialize random weights and we never update them. So we want to make sure that this initial dense network, this network is actually rich enough so that we can find these subnetworks. And for that, what we use is for each layer, we actually sample weights from this set, only from like these 2 values. This sigma is actually the standard deviation of the K-Bing normal distribution for that layer. And it has been shown in actually some prior work on centralized setting that with this distribution, empirically, we actually achieve better performance. And also using this distribution with like a support size of 2 makes our storage very efficient. So after training, after like we finalize federated learning, we end up with a dense network that is actually frozen from the beginning and a binary mask that we actually extract during training. So all we need to store is these 2 values. And for that, what we need is actually a random seed to extract the dense network and a binary mask, which takes less than 1 bit per parameter. So it's actually like there's a huge saving in memory cost after training. And a second property is at inference time, when we actually extract this subnetwork and use it for inference, each parameter is either 0 because it's not a part of the subnetwork, or if it's a part of the subnetwork, it takes one of these 2 values. So we have a ternary representation here, and there are prior work, mostly like hardware-oriented work, that shows like some computational efficiency when the parameters are ternary or binary. So we also believe that it actually leads to some efficient inference, like finding these random subnetworks. So to show some empirical results, so we compare our method, we call it FEDPM, Federated Probabilistic Mask, to some other compression methods. So except FedMask, all the other baselines are actually training the model parameters as usual. And at communication time, they apply like all sorts of compression techniques like quantization or sometimes like some projections. And one common thing among all of them is they operate around the same bit rate. So if you look at the right plot, they are all close to 1 bit per parameter. FedPM, our method, is actually on average across rounds achieving a smaller bit rate than rest of the baselines. And if you look at the test accuracy, our method is actually able to converge much faster than all our other baselines. And it also achieves a higher accuracy. So I think this result is surprising because without like actually running these experiments, I wouldn't expect our method to perform better than the baselines that are actually training the parameters. Because all we do is we randomly initialize a network and we find good subnetworks and we hope that it will work. And it's actually working better than, like, for example, QSGD is one of the strongest baselines and it's outperforming QSGD. And there's a fast convergence here. So this was the result on CIFAR-10 dataset. And we observe actually more significant gains on CIFAR-100, a slightly more difficult dataset. And in the paper, you can also see our result on MNIST and eMNIST. I'm skipping those results for the sake of time. And yeah, so the results I showed you previously are on IID dataset with full participation. So it's not the most realistic scenario, but here we are actually, so we tested like various combinations of non-IID level and partial participation level. So for example, when rho is 1, we assume that all clients participate at every round. When rho is 0.5, only half of the clients participate. So this is, for example, the most difficult setup. And this Cmax is actually indicating like for each client how many classes they can see in their data set. So this also indicates non-IIDness level. So overall, this is the, I think, most difficult setup. And if you look at like all combinations, we have sometimes like up to 10% gain, even sometimes more than 10% gain in accuracy compared to like other baselines. So this is the accuracy result. We can also compare the bitrate, and in terms of bitrate, these two baselines are very close to our methods, Drive and Eden. But if you look at the accuracy, there is like sometimes 20% difference between FedPM and the baseline. So this was a quick summary of our work. Maybe a few notes I can add here. So when we were actually like working on the iClear submission, we weren't using a Flower code, and at the submission time, we had some difficulty in scaling up our own custom FL code. But then after the submission, we were like, okay, so now we have time, let's write this code properly. And we switched to Flower, spent some time, and everything just became much easier. We didn't even have to worry about anything like scaling to like more than 1,000 clients, or like scaling the model size wasn't a problem anymore. Before, in our custom code, we had a lot of memory problems. So I think that was one factor why we were able to finish the follow-up work in limited time. So yeah, if you have any questions, I'm happy to answer. You can check our paper on arXiv. You can check our code. We will update our code base with the Flower implementation very soon. Thank you for listening.
Thank you so much. This is a great talk, and I'm happy that you found Flower helpful in your research. That's amazing.
Really helpful. Yeah. Thank you. Thank you.
Great. Well, I see we've got a couple of questions. Let me just look at one question we got in was, they say you showed results going up to CIFAR 100, and they're saying that, I'm paraphrasing here, but they're basically saying that doing these experiments can be difficult. Given your techniques, what type of experiment do you think might show its gains best? I guess they're getting at the fact that running experiments on different data sets sometimes is a bit problematic. But is there a type of scenario or a scale of data set where you think your methods would sort of shine even more brightly than they do?
I see. So I think so one thing our method is exploiting is over-parameterization. So as the model gets more over-parameterized, our methods, I think, will work better. So for example, in our MNIST experiments, we realized that like with slightly larger models, we were getting more significant gain over the baselines, because we are basically trying to find subnetworks. So the original network should be large enough, and there must be some redundancies. So we didn't empirically observe any difficulty like across data sets, but for each data set, we observed that the model should be over-parameterized enough so that we can actually find a subnet, like a sparse solution to the problem.
Oh, I see. I understand. Actually makes sense. And let me just see if there's any more questions. Feel free, everyone, to you can enter in Slack or into Zoom.
I have a follow-up to that, what you mentioned. So did you explore, for example, you benefit from an over-parameterized model. So did you study how long does it take to amortize the initial communication cost of having this maybe potentially much bigger model and a very small model I can train from scratch? Did you put that into a plot, for example?
So I don't have those plots here, and we don't have them in the paper either. But so what we observe here is, for example, we used a 6-layer convolutional network on CIFAR10 here, and we are able to achieve this performance. If we were to use a smaller network, that would give maybe the same bit rate. The accuracy is actually smaller.
Okay.
Yeah, so it's not something like we over-parameterize the network just to show some improvement. It's actually really improving the accuracy, like taking that path.
Okay, yeah, cool. Yeah, very interesting. Also, I have a follow-up, slightly unrelated question, but also very relevant, I think. So the clients locally, they are extracting a submodel from the peak model effectively, right? When they are applying the mask. Have you considered, for example, imposing some structure on how this masking is, so you can take advantage of, for example, some training efficiency? Because if you're extracting like a random model, those let's say random sparse multiplications are difficult to accelerate. But if you have a structure.
Yeah, that's a really good point. So I guess what you're trying to say is like we have a probability mask and we extract a binary mask, but there's no structure here. So when we do the forward pass, we are not gaining any training efficiency. So this is one of our actually in when I present this paper, usually I have this like final slide where I mention future work, and this is one of the future works. I think it's a really interesting question. We don't know, of course, like if it would still perform well if we impose a structure here. It's, I think, very open. I didn't see any work on that. So I think we just need to try it. Like, if there is a forced like structure in the binary mask, I don't know if we will still get the same performance. But yeah, of course, it would come with computational efficiency at training time. And I think it's very relevant, like given that clients have only limited compute power.
Yeah. Cool.
Great. Well, I see one last question. It's quite simple. The person's just asking, have you seen any instances in your experiments where your method has an impact on fairness?
Oh, that's a good point. We didn't check that. We never checked fairness. We only look at accuracy and bitrate so far. But that's a really good point. Yeah.
Yeah, that's very reasonable that you can't test every condition. I guess they were just curious. Okay. Well, thank you once again. Thank you very much for the presentation. It's been great to see you again. Great to see this wonderful work. I think it really it provokes a few interesting questions about how we can make federated learning more scalable moving forward, and how we can exploit some of these these sort of interesting results that have some sort of a bit of a theoretical underpinning to them too. So that's great. So thank you so much.
Thank you so much for having me. Thank you.
Cool. Well, I will reshare my screen and introduce our next speaker. And you've already heard from him a few times already in this monthly session and even in prior monthly events. His name is Javier Fernandez Marquez, and he is freshly joined Flower Labs. So welcome, Javier, as a member of Flower Labs, but also perhaps more importantly, welcome to Flower Monthly to tell everyone about how they can squeeze out their last little bit of performance when they want to run a simulation because, I don't know, a NeurICLR deadline is looming, or they just need to understand how this method is going to work in production, perhaps when they scale it out. So yeah, thanks for joining us today and telling us about simulation.
Yes, of course. Happy to tell you about it. Okay, can I share? I'll share my screen. Can you see it?
Yep, looks great to me.
Okay, okay, then let's start. So in this talk, I'm aiming for roughly 20 minutes. And what I want to tell you about are a common set of tricks or ways of working with Flower that I usually use in my projects, at least for the last 2.5 years or so that I've been using Flower for either demos or papers. So let's start directly. All the code I'm going to be showing some snippets of code, and I won't be going into them in all detail. I will only highlight some lines of code, but all the code is now in this repo that you can load and play with it, either during the talk or after the talk. And also, just to make some publicity, we're increasing our activity in Twitter, so feel free to follow us. And if you have any questions, technical questions, or you just want to join the Flower community, feel free to join our Slack channel. So I'll start by giving 3 examples of how you can configure your strategies in Flower. But before jumping into it, I'm going to explain very briefly what a strategy is. So you can think of a strategy as the director of an orchestra, where the orchestra is the federated learning experiment you want to run. And in that way, the strategy orchestrates different stages like sampling clients, deciding how we aggregate the updates that the clients send back to the server, and other aspects like, for example, how we are going to evaluate the global model after the aggregation. So one cool thing you can do with Flower very easily is to change how we sample clients. By default, the clients are sampled by uniformly sampling all the clients that are currently connected to the server. But in some situations, you might want to change this. For example, here, what I'm changing is in the first round, I do random sampling, but then in subsequent rounds, what I do is I have defined a variable that I call keep ratio that will set some clients to be resampled in the following round. And here I'm doing exactly that. I'm maintaining some of the clients, and then the remaining clients are sampled as usual using the client manager. You can override configure fit method in your strategy to do other type of sampling. For example, you can sample clients based on their CO2 emissions at a particular point in time. This was presented in the Flower Summit last week. Or you want to also override this method to send specific instructions to different clients. For example, you might have highly capable clients, so you want to send them a big model to train. More constrained clients, you might want to send them a smaller model to train, or a smaller version of the bigger model. So these are some examples of things you can do when you customize the configured method in your Flower strategies. Another method you can change in your strategy is what is called aggregate fit, which defines how the updated models on the clients are aggregated to generate a new global model. For example, in this strategy, I'm inheriting from FedAverage, but let's say I want to implement a method that stochastically drops a certain percentage of the updates. One reason why you would want to do this is, for example, to simulate scenarios where clients fail. So these updates are never sent back to the server, or you want to simulate a communication channel failure. You can even do more sophisticated things. For example, you can once you get the model updates from the clients, you can assign different weighting to each of them based on, for example, an auxiliary data set you have in your server. You can do that here. Or you want to implement a brand new aggregation methodology based on potentially previous states of the global model. These are some things you can do when you change the aggregate fit method in your strategies. And usually at the end of every round in Flower, we need to evaluate the new global model that has just been created from the aggregation stage. By default, this happens after every single round, but in some settings, you might want not to do it after every single round, because, for example, maybe the convergence rate of your experiment is not so fast, so you would only observe changes every, let's say, every 5 rounds or every 20 rounds, or even every more rounds. So in this snippet of code, I'm changing exactly that functionality. I'm saying, okay, I want to run the evaluation of my global model according to the variable I have defined called eval every n, which I have set up to be by default 5. So these are 3 methods. Normally you want to consider modifying your Flower strategies to better help you with your experiments. Now I'm gonna still talk about the strategies and a bit about the clients, but in 2 particular use cases that some people are really starting to look into with a lot of detail. And one of them is to send multiple models to the clients instead of a single model, which is the typical setup in federated learning. And also I will be showing you how you can retrieve metrics from the clients very easily, because normally clients, we only care about the model updated on the clients and how it is used on the server, but we can send additional statistics that might be helpful in simulations. So let's say we want to send multiple models. One scenario where we would want to do that is if we want to do some form of knowledge distillation on the client side. So for that, the model we train in federation would be the student, but we still need to give the clients, we need to give them a teacher, and a pre-trained teacher, to be exact. So how can we send this model to the clients? Well, the easiest way would be to incorporate this teacher model into the instructions we send to the clients. So one obvious way of doing it will be to override the configure fit method in your strategies that, as we saw earlier, is also in charge of sampling clients. But here we don't touch that part, and instead we add additional components to the config dictionary. In this case, the teacher model, as well as some parameters for performing the knowledge distillation stage. Then the clients that have been sampled in this particular round will receive, as usual, the model that is being trained, that is being federated, in this case, is student, as well as a dictionary that here it is called config that contains the teacher that we can use, and we can instantiate it and then pass it to our new training function that will be doing some knowledge distillation. So this is an example on how to send multiple models to your clients. For distillation, makes sense to work like this. In other settings, for example, you might want to do multimodal training, where you have one model that looks maybe to the images in a video and another different model that looks into the audio of the video. So you would use a similar formulation to make sure that these 2 models can be trained by your clients. And then last but not least, usually the way the fit method returns has the following signature. So we send the model, the parameters that have been updated by the clients. Typically, we send how many training examples were in the local data set. This is a statistic typically used by FedAverage, but it's not compulsory. And there is another third element that is by default an empty Python dictionary, where you can add anything you want. Ideally, you would be adding small bits of information, like, for example, I want to time how long it took to do local training. Another thing you could send, for example, based on the previous talk, you could send the statistics of the sparsity ratio of the masks that the clients use within every batch, for example. So that information can be sent in this Python dictionary. And then how do you get that information back in the server? So you would need to look into the aggregate feed method in the strategy, because it's the one that receives the updates from the clients. And then you can retrieve this dictionary, Python dictionary, which is called metrics in the Flower API. You can retrieve it like this. So this is one very convenient way of using the metrics in Flower. And now the last block or the last part of my talk is going to be about how to run Flower simulations effectively. And the idea of Flower simulations with FL simulation with Flower is that you can run exactly the same code, whether you are developing on your laptop or you are running it on a GPU server you might have on your lab, or even if you have access to a multi-node setup in your data center, you can still reuse exactly the same code. So I think probably I don't need to motivate a lot why we want to do simulation in FL. But if I have to highlight two main reasons is, one, normally we cannot have access to a large number of clients. For example, maybe we can, if we are very lucky, we can have access to 10, let's say, smartphones or 10 Raspberry Pis, maybe 100 if we are super lucky. But it's not realistic to have access to several thousands. Not to mention the cost of managing them. So we can simulate very easily clients as simple standalone Python processes. So this is what simulation allows us to do. And this is what the virtual client proxy in Flower exactly does. The virtual client proxy makes use of another toolkit to launch virtual clients in a resource-aware manner, which also allows you to very flexibly scale to much larger systems to run your federated learning workloads. And this dynamically scaling of your workloads is exactly the point I'm going to be talking about in the following 2 or 3 slides. So let's say that you have written let's say you already have all your Flower code that you run on a few devices, maybe through the standard gRPC API. And now you decide to work in a simulation setting. You don't need to change anything in the code except how you start experiment. So instead of having a start server, you will have this line, start simulation, which requires one additional argument called client resources, which is a standard Python dictionary where you need to specify what are the number of CPU threads you would like to allocate to every client participating in the round, and what is the ratio of GPU resources that this client needs. So for example, if you have a laptop with 10 CPU threads and you want to run 10 clients in the round, if you said that every client needs 1 CPU thread, you can run all the 10 clients concurrently at the same time within the round. But for example, if your clients are too computationally expensive because maybe the model is a bit larger, you would be better off allocating maybe 5 CPU threads to every client. So this means that you can still run a round with 10 clients per round, but instead of all being running at the same time, they will be running 2 at a time, right? 5 CPU threads will be spent by one client, another 5 will be used for another. Once one of these clients finishes, another client will be spawned and do their local training. And this will happen until the round is completed. Let's say that you now have access to a system that you have GPU resources. So a similar logic can be applied to this setup. You can have a large, let's say a memory-intensive training pipeline. For example, here I'm federating a Vision transformer for ImageNet with a reasonable batch size, 64. And because this has a fairly large memory footprint, I have decided I can only afford having 2 clients in my GPU. Here, what I'm stating is that every client should be allocated half of the GPU memory resources. If on the contrary, my let's say my federated learning research, let's say my new strategy I'm developing allows for clients to train with a much smaller batch size. For example, here I have reduced it to 8. Then you can afford reducing the resources needed for every client. And as it is the case here, I'm able to pack 8 PAT clients at a time in the same GPU. This, of course, comes with different implications. Some of them are positive. Usually, the more clients I can pack concurrently, the faster my simulation runs. But you need to bear in mind that that can likely lead to more memory usage. For example, here you can see that my memory utilization is close to 22 gigabytes of system memory, and here is double. So these are some factors to take into account. But let's say that you're super lucky and you have access to multiple machines, not a single machine with GPUs. So how do I interconnect all these machines together with Flower? And the way to do this is by using simulation in a slightly different way. Normally, when you launch a virtual client engine, a server for the Ray toolkit is being created behind the scenes. But when you want to interconnect multiple nodes, it's better to do this process in a different way. So for example, what you need to do is to change your code. So you specify the initialization argument for Ray to set the address to auto. And what this means is that when you launch the code, it will look for an already running Ray server in your system. How do you launch the Ray server? You just go to your terminal and you can do Ray start -- head. That will create the head node of your system. Then you open another terminal, let's say on your second machine or all your machines you have. And then you just need to copy the line of code shown in the message where on the terminal you initialize the head from. Copy it, and that will ensure that that second node is attached to your head. So which means that the virtual client engine will be able to see the complete pool of CPU and GPU resources available. And then you can go back to your main node and launch the experiment as usual without any change in the code. Of course, the moment you start running parallel jobs, the moment you start adding new machines, the moment you want to run things at the highest possible efficiency, you need to take into account certain considerations. One of the main aspects is to understand, okay, what is the memory footprint and compute footprint that my clients require? How much VRAM my model needs? Once you have understood that, you can set what are the CPU and GPU resources that every client will need. What if I want to run things even faster? Well, maybe you need to understand first where the bottlenecks are. Are the bottlenecks the lack of concurrent clients running on the same GPU? Or is the bottleneck the way I'm accessing the data set in my file system? And finally, as I mentioned, when you work with simulation, you are working effectively with two different tools. We have the open source framework Flower as well as Ray, and they have been evolving in slightly different ways. So it is so in my advice is that for the best experience is not to use the absolute latest version of Ray, but instead use an earlier version that is not so old anyway, which is the one I highlight here with this command. In simulation, sometimes maybe your experiments will fail because your client is reading data from not the right directory, for example. So before launching the experiment again, you want to ensure that there are no hanging processes in your system. So you can stop everything running this command Ray stop -f. And also if you encounter any issue or if you have a new cool feature about how you use simulation in your experiments, feel free to reach out to me on Slack. If you have an issue, reach out to me anyway or anyone in the team, or open a GitHub issue with a simulation label. This is everything I wanted to share. once again, you can find the code for all the experiments and all the ideas I've been highlighting in this talk. And I'm very happy to take questions if there are any.
Thank you. Another great presentation. I've got to say this has been a sort of a hot button issue for people on our Slack lately. And so it's great that you took some time out to describe, albeit at a high level, some of the approaches to getting the most out of the simulation engine. Let me see what questions I can see. Okay, one person is asking, they're basically saying they have this Ray version thing that you mentioned, fine. But if they, what do you do as an experienced user when you run out of memory? So they're running the simulation, it's not an issue to do with this Ray thing, but then the thing blows up. It's like they're getting out of memory errors. What can they do? I guess they're kind of getting at what can they do to debug the issue? Where do they start?
Yeah, yes, it's a good question. So what I generally do is basically my first point here. Sometimes like you start a new experiment and you have a rough sense of, oh, this is a big model or this is a small model, but big or a small model, basically the moment you want to parallelize things on GPU, even a few megabytes make a big difference. So my advice and what I generally do is let me run simulation with one client per round. And with that, it allows me to see, oh, with one client per round, this is how much memory a single client needs. And it has access to the entire GPU. So based on that, okay, I can see that I'm using 2 gigabytes. I have 8 gigabytes on my GPU. Well, technically, I should be able to pack 4 in concurrently, but that might be pushing it too close to the limit. So maybe realistically, I can only pack 3 or 2 because the global model also needs to run somewhere. So that is my advice. The first advice. The second advice is make sure that your clients are not maybe recording any unnecessary data on the GPU. Maybe you are keeping track of the activations and you forgot to send them from GPU down to CPU. This is a very typical issue that might arise if you are starting to debug something and then you forgot to remove that line of code, for example.
Sure, that makes sense. I guess as a follow-up question, there was one just saying, what is your favorite method for profiling memory usage?
My favorite method to profile memory usage is, for sure, NVIDIA SMI. If I need to go into much finer resolution than what you can see in NVIDIA SMI, I've been using the PyTorch profiler a lot, but I do that generally outside of federated learning. Like you can use a PyTorch profiler in isolation with the model you are trying to federate, and maybe you can see, and you will be seeing at very fine resolutions what is the memory peak of every stage of your model.
I see. So you're doing that in a centralized setting to get a good feel for the memory sort of bottlenecks and where they are and so on, and that informs when you kind of go back into the federated world.
Yeah. Yes. You don't need to design a complete centralized federated centralized setting. You just need to get your model and maybe even just passing some batches of data through your model. That's enough to capture the memory signature of your model.
I see.
That's what I would do, at least.
I see. Cool. Let's see if anything else. I guess we'll make this the final question. And they're saying, what's the I guess what is the largest simulation that you've run personally? Like, I guess maybe number of clients and the amount of data set, or what's the largest?
The largest, probably 4 GPU machines. So 32 GPUs, and likely concurrently maybe 8 clients per round. No, 8 clients in every GPU, so 8 by 32 clients concurrently running. Probably the largest I've recently run, for sure.
Oh, so it's like 4 racks of 8. So
no, for both. Yes. 4 racks of 8, yes. 4 machines with 8 GPUs, each of them.
Yeah, 4 machines with 8 GPUs each, 32 GPUs.
Yeah, and like big GPUs, and then you can very easily pack even fairly big models. You can pack several within every GPU.
Oh, I see. Okay, I guess that must answer their question. I guess they're curious what you've been up to. Yeah, well then we're sort of running out of time for Flower Monthly now. So if you stop sharing, I will share our
sharing.
I'll share our. Oops. Let's see if I can do this. And does everyone see the screen?
Yes.
Great. Well then, this is the end of Flower Monthly. I just want to say thank you everyone for coming to Flower Monthly June. Our next Flower Monthly will be July 5th. That's the first Wednesday of July. It'll be 4 p.m. UTC, so the same start time that we had this week. I want to say thank you very much to Berivan and Javier for 2 wonderful kind of like completely separate, on the different spectrum talks. One, deeply researchy, really interesting stuff. How do we build on lottery ticket hypothesis, and how do we build the next generation of FL methods? And then we had Javier talking about what are the nuts and bolts. How are we going to do that practically speaking? How do we scale these things up? How do we just get to A to B right now when we want to do a simulation? So 2 really useful talks here. So thank you both so much for being with us this month. And I'll just conclude by saying, let's see, we have the Flower Monthly Slack channel. If you're interested, you can catch up with all of the different videos of Flower Monthly. So this event will get posted in the coming weeks or so. We've got a bit of a backlog from Flower Summit naturally. And so the video of this event will be posted. You can find it on our YouTube channel. You can also find it on this website that you see listed on this slide. Join the Slack if you haven't done so already. And then one new addition that we haven't really advertised too much yet is that we have a calendar of events. So it's a Google Calendar, I believe, where you have all the various Flower events are populated there. So if you're kind of curious, you want to get a reminder for when Flower Monthly is, it's a great way to see Flower Monthly in your own time zone and not get confused. You can subscribe by following this URL, this nice friendly URL of flower.dev/Flower events calendar. So that's all the announcements. Thank you everyone for joining us, and I will catch you all next month. Take care.
Thank you.
Thank you.
Yeah.
Thank you.
Bye-bye.
Bye-bye.
Bye.